Hello, Moses here. How do we determine the direction of equilibrium of a reaction, whether it's going to favor the products, whether it's going to favor the reactants? One way is to use pKa values. Okay, here I have a pKa table. Let me give you an example. Let's say that you are reacting water with HCl. Simple reaction. That's a strong acid, we know, because you see the pKa value is quite low. You know that the oxygen is going to take that hydrogen, and then the bond between the hydrogen and chlorine will break. We are going to get hydronium, H3O plus, H2O, and hydrogen gives you H3O plus and Cl minus. We did that in an earlier lesson. Now we know that the pKa of hydronium is negative 1.7. Remember, I'm just focusing on the acids. This is the conjugate acid, and this is the parent acid right here, because it's donated a proton to water. Water is going to play the role of a base. The Cl minus is going to be the conjugate base. So let's focus just on the acids. Hydronium pKa right here is negative 1.7. HCl pKa right here is negative 6.3. Equilibrium lies on the side of the weak acid. The lower the pKa, the stronger the acid. This will be the stronger acid of the two. This will be the weaker acid. Hydronium itself is not a weak acid. I'm just saying it's a weaker acid. So I predict the equilibrium will go this way. That is method 1, using the law that equilibrium always lies on the side of the weak acid. Method 2 is by using this equation right here, finding the value of equilibrium constant. If it's going to be greater than 1, then products are favored. If it's going to be equal to 1, then you are at equilibrium. We need to use this arrow. So product favored, that arrow. If it's less than 1, then most likely we are going backward, reverse. So the formula is 10 to the power pKa of the product acid, which is negative 1.7, and then we're going to subtract the pKa of the reactant acid, which is negative 6.3. If you do the math, you will get that Q will be 39,810.72. Well, this is way greater than 1. The reaction is sure to go forward according to that rule. So those are two ways on how to do that. Let's do another example. Here's another example. Determination of the direction of equilibrium. What is the predicted direction of equilibrium in the reaction below? Our reaction this time around is involving acetic acid and H2O, using H2O as a base to take out that hydrogen and the lone pair between OH going to the oxygen. Our product, if this reaction happens, our product will be an acetate, the conjugate base, and hydronium. Now let's use method 1, the pKa method. Reaction lies on the side of the weaker acid, the one having a higher pKa. So water has hydronium, has negative 1.7. Acetic acid, which is this, is 4.76. Those are the pKa values of the two acids. This plays the role of the acid on the left. This on the right is the conjugate acid. Obviously, it has a plus charge on it, signing an acid. So by method 1, the reaction lies or favors the side of the weaker acid. So this one having a higher pKa will be the weaker acid. The higher the pKa, the weaker the acid. So we expect, according to method 1, the equilibrium will be favoring reactants. In fact, you should say equilibrium lies to the left. Method 2, yes, let's use the calculation method and really find an estimated KEQ value. KEQ equals to 10 to the power of, now we need to subtract the pKa of the product acid minus pKa of the reactant acid. The product acid is negative 1.7. The reactant acid is positive 4.76. If you do the calculations, you'll find that KEQ equals to 3.46 times 10 to the power minus 7. This is way less than 1. So again, if the KEQ is less than 1, then the reactants are favored. That's another way to do it. Let's do another example. Determination of the direction of equilibrium. What is the predicted direction of equilibrium in the reaction below? We have a phenol, and then we're going to react that with sodium hydroxide. We know that sodium hydroxide is one of those strong bases, so we can already call this a base, and this has an acidic hydrogen sitting on an electronegative element. Oxygen, of course, there's resonance stabilization. This is gonna be an acid. We want to know if this reaction will go forward, if it will be at equilibrium, or it will be going reverse. So let's use this as a base. We take out that hydrogen, push the electrons on the oxygen, so OH and H gives you water. Okay, now on the product side, this will be the conjugate base. Of course, the negative charge tells me that, and then the water is gonna be the conjugate acid. Part of the structure of the water came from the base, so we call it conjugate acid. Okay, now pKa of phenol is 9.9 given. We know that the pKa of water is been proven at 25 is roughly 14. Most authors will say 15, but I'm just gonna use 14 for purposes of explaining. So let's determine using method 1. The equilibrium lies on the side of weak acid. If you look carefully, you'll see that the water has a higher pKa than the phenol. So the equilibrium is likely to lie on the right side. So using method 1 of comparing pKa's, where equilibrium lies on the side of the weaker acid, water here being the weaker acid of the two between water and the phenol. So equilibrium is predicted to lie on the right side. Okay, so we're going to say, using that method, equilibrium lies toward the products. Favors formation of product. Lies on this right side, favors formation of product. Using method 2, we can use the formula here to find the estimated value of KQ, which is 10 to the power of the difference between the pK value of the product acid and the reactant acid. The product acid is water, so we'll say it's gonna be 14 minus 9.9. If you do the calculations, you'll find that the KQ value of this reaction is 12,000 589.25. That is way greater than 1, proving method 1, that the equilibrium will lie to the right. Products favored. I've shown you 3 examples on how to use pKa values to determine this direction of equilibrium. See you for another lesson. Bye.